Good morning. We are going to start the complex integration, and it is including the topics, the definition of complex integration, then the Cauchy's integral theorem, and then Cauchy's integral formula, and then the Taylor series and Lorentz series. We are going to discuss all these in this section. And first we are going to start the introduction to the complex integration. Now here we are considering this fz to be the continuous function of the complex variable z, and z is x plus iota y. It is depending upon the complex variable z. This variable z is defined on all the points of this curve C, having the endpoints A and B, right? And let's divide this curve into these n parts. I have divided this curve into n parts. At the points, we have taken first point A, the initial point, to be P0, and then P1, then P2, then Pi minus 1, then Pi plus 1 up to Pn, right? Now this P0 is having the variable Z0. At this point, let the variable be Z0. And at P1, we are having the variable Z1. Then at P2, we have the variable Z2 up to so on, right? So we have taken the point A to be P0 Z0, and then we have the point P1 Z1. P0 is representing the variable Z0, P1 is representing the variable Z1, and then so on. Pn is representing the variable Zn. That point is taken to be as the last end point, that is B. Now if suppose this Pi is representing the point Zi, and this Pi minus 1 is representing the point Zi minus 1, then what is delta Zi? It is the difference of Zi minus Zi minus 1, right? And if suppose this Xi is the point on the arc Pi minus 1 Pi, on this arc if we are having this point Xi, then the limit sum, that is if I take the summation of f of Xi delta Zi, this summation is for I equal to 1 up to n. If we take the sum of all these, right, as n tends to infinity and delta Zi tending to 0, if it exists, if for these two conditions this sum exists, then this is called the line integral of fz along this curve C. So if it exists, then it is called the line integral of fz along the curve C. And it is denoted by the line integral of fz dz over the curve C, right? And now we are moving to the new term, that is the contour integral. What happens if this point A is coincide with the point P, which means the curve will be then the closed curve. The point A is coinciding with the end point B. So this curve will become the closed curve, right? So in case the point P0 and the point Pn coincides, then C is the closed curve In this case then, the integral is called the contour integral. It is called the contour integral, and how it is denoted? It is denoted by the closed integral fz dz over the curve C. This sign means the curve is closed curve, right? Now if fz is equal to uxy plus iota vxy, then since dz will be dx plus iota dy, because what is z? Z is x plus iota y, then dz will be dx plus iota dy, right? Then we have this line integral to be equal to, the line integral of fz dz over C will be equal to the line integral of, just put the value of fz over here, that is u plus iota v, right? And dz is dx plus iota dy. So that is further equal to the line integral of u dx plus iota u dy plus iota v dx minus v dy. Separating the real parts, we have u dx minus v dy, right? Plus iota u dy plus v dx. Separating the integrals, now we are having the two line integrals for this integrand and plus iota the integral for this integrand over the curve C, right? So this shows that the evaluation of a line integral of a complex function can be reduced to evaluation of two line integrals of real functions, right? And moreover, the value of this line integral depends upon the path of integration, unless the integrand is analytic. So the remark is written over here, the value of integral depends upon the path of integration unless the integrand is analytic. Analytic function means if it is differentiable at every point in the open set, in the open region, right? Okay. Second point, the second remark is the integration of fz is equal to the negative of integration of fz dz from the points B to A. If we interchange these points, we got the negative sign with the integration. And third remark, if C is the point on the arc joining A and B, this is the arc, and C is the point on this arc, then the integration from A to B fz dz will be equal to the integration from first A to C fz dz, and then the integration from C to B. We have the sum of these two integrals, right? So here ends up the first lesson. In the next content, we are going to do some examples. All right, thank you.